Welcome to this session that is going to be looking at celebrating 30 years of PET in Australia. My role is to give you the history and background that led to PET being introduced into Australia in 1992. It is, however, a story mostly about the cyclotron rather than PET, and we will go through the background and history up to the point of bringing the cyclotron to Australia. We all know that radioactivity and the knowledge about it started in the late 1800s, 19th century, when Henri Becquerel left some ore near a photographic plate and found that it exposed the plate when he developed it. He thus discovered natural radioactivity. So experiments were then conducted and treatments started using radioactivity within a few years, when people realized the damage that it could do to tissue. Our story about the cyclotron picks up in around 1928, where a Norwegian engineer called Rolf Widerøe invented the first device that could accelerate a charged particle, which he referred to as the betatron. And he used radio frequency pulses to accelerate beta particles in the presence of an electromagnetic field. This was picked up by Ernest Lawrence in Berkeley in early 1930s, and he further develops this idea of accelerating particles to achieve high velocity and high energy, and creates the first cyclotron. It was only 12.7 centimeters in diameter and only accelerated deuterons to 80 keV, but this was the first time that particles had been accelerated and thus could be directed at a target to produce artificial radioactivity. Before this, any radioactivity that had been used was either natural, from radium, for example, or had been artificially induced by neutron irradiation. Lawrence continued to develop his ideas, and in 1936 he built the 94 centimeter diameter cyclotron, which was able to produce the first artificial element, technetium. Technetium is not found in nature because all of the isotopes are radioactive and therefore have decayed away since the creation of the Earth's surface. So this was a gap in the periodic table that Lawrence was able to fill by producing technetium. He is at this time joined by his physician brother John Lawrence, and we'll see how important this is in the development of nuclear medicine in the next few slides. Ernest Lawrence went on to receive the Nobel Prize for his development of the cyclotron in 1939, and you can see that he just keeps building bigger and bigger cyclotrons. While all this was happening, at the same time, the endocrinologist and physiologist Saul Hertz, who we all know about, made inquiries of the MIT president Carl Compton at a luncheon at MIT about whether iodine could be made radioactive artificially. Hertz knew that the thyroid gland concentrated iodine, and wondered whether the radioactive iodine could be used to suppress overactive thyroid function. The knowledge about the iodine in the thyroid gland had been known since the 1850s and 60s, but Hertz was the first to conceive of this thought to use a radioactive iodine. As you can see in the letter on the right-hand side, Compton wrote back to him after a little while and said, yes, of course this can be done. We can make a form of radioactive iodine, but he points out that the one that they would have made, he doesn't say which, but he points out that it only had a 25-minute half-life. So this was made again by neutron irradiation, and clearly was probably not going to work for Hertz's experiments. Nevertheless, he's able to use this to study radioactive uptake in rabbits with a probe. Back in Berkeley, on the other side of the US, the brother of Lawrence, John Lawrence, has started to think about using phosphorus-32, which he knows to concentrate in the bones. to treat a patient with chronic lymphatic leukemia. This is probably the first example we have of a radionuclide therapy using what would be considered today a standard approach of a systemic injection. This was made in the cyclotron that his brother Ernest had built. In 1940, MIT continues to investigate radioiodine and receives a small grant of $30,000 from the Markle Foundation in New York to install a cyclotron, which they indicated would be primarily for medical use. So you can see that very early on, the cyclotron has started to be targeted for use in radionuclide imaging and therapy. This is important because at this stage, the nuclear reactor has not yet been built and no nuclear fission reactions have been undertaken. In 1941, MIT uses their cyclotron to produce a radioiodine consisting of 90% iodine-130 and roughly 10% I-131. And in the same year, the first Massachusetts General Hospital patient was treated with 80 megabecquerels of radioiodine for hypothyroidism by Saul Hertz. The following year, 1942, Enrico Fermi undertook the first controlled nuclear fission reaction under the squash courts at the University of Chicago. Lawrence continues to work on the cyclotron, and his final one is a 4.7 meter diameter cyclotron, which could accelerate deuterons to over 100 MeV, and you can see the size of this massive device in the photograph on the right. This is followed by great interest in the cyclotron for medical uses, and in particular for producing neutrons for neutron radiotherapy. The first dedicated medical cyclotron for in a hospital for that use was opened by Queen Elizabeth II at the Hammersmith Hospital in West London, which had been installed there by the Medical Research Council of the UK. So what was happening in Australia at this time? Well, we weren't too far behind the introduction of radionuclides in medicine compared to the US. The Australian Commonwealth X-ray and Radium Laboratory in Melbourne in 1947 placed its first order for iodine-131 from the US. This was on the back of the Manhattan Project and the rapid development of nuclear fission, leading, of course, to the A-bomb used in Japan in the Second World War. But the American Oak Ridge facility, where a lot of this was developed, also knew about the potential for use in medicine and had started sending iodine-131 to countries that had bilateral relationships with it, where they could exchange such material. The initial order of 1,500 megabecquerels of radioiodine-131 was sent by sea because the cost of flying it was prohibitive because of the very heavy containers that were thought to be needed to encase it in its transportation. So I think the first order was for approximately 20 pounds for the iodine-131, but the flight would have cost another 200 pounds. So it was elected to be sent by sea, and of course by the time it reached Australia and they got it into the laboratory to check it, only about 100 kilobecquerels was remaining, so it wasn't very useful. But soon after this, you can see that regular air deliveries of iodine from the US to Australia commenced. So we see, if you look at the history book that the Society published a few years ago, there are a number of references to various centres starting to use radioiodine for investigation of thyroid function in Brisbane, in Melbourne, in Launceston. I'm not sure about Sydney at this stage. And a few years ago, when I was president, I was helping to clean out the archives of the Society with the general manager, and came across the book you can see the cover of here, which was Ken Clark's MSc thesis. Ken was one of the first medical physicists in the country, and certainly the first to work in nuclear medicine. He was working at the time at the University of Melbourne, and this was his master's thesis on problems associated with using radioactive iodine. I found this original copy buried in our archives from 1953 when he received his master's degree. So in Australia, of course, the nuclear reactor program really commenced in the 1950s under the guise of the Australian Atomic Energy Commission, as it was called at the time, or the AAEC, and we built HIFAR, the high flux atomic reactor, which first achieved criticality on Australia Day in 1958. Around 10 years or so later, radioiodine was being produced in medical specification, which was then supplied for treatment, and we thus had our own domestic supply. At around the same time that the AAEC was pushing very hard on the development of technetium label compounds as well, in particular bone scanning and lung scanning compounds. Of course, today HIFAR has been decommissioned and we have OPAL, the Australian Open Light Water Reactor, and that is serving our domestic needs for all of the reactor-based isotopes. However, we still didn't have a cyclotron. The image that you can see here is the cover of a conference proceedings from 1962 from a meeting sponsored by the US Atomic Energy Commission. And the front cover is a bone scan using fluorine-18. So while it's not coincidence detection, or certainly not tomographic, it at least shows the early application of positrons in medicine. And I thought that this table of potentially useful radioisotopes for scanning from the same proceedings was particularly useful because really we wouldn't, if we wrote this list today, I don't think we would change very much. You can see gallium-68, fluorine-18, copper-64, zirconium-89, iodine-124, all of the things that we would like to have readily available to us and are becoming increasingly available here in Australia. It points out that gallium-68 is easily prepared by milking germanium-68, and really it's a very astute list coming from 60 years ago now. What about local activity? Well, Professor Rutherford Blackburn, or Blackie as he's been known for many, many years, returned in the late 1940s from Columbia Presbyterian Hospital in New York, a university, where he worked with Professor Loeb of famous textbook of medicine fame. And they had been starting to use radioisotopes in medical investigation, clinical trials. And so Blackie was keen to establish a similar unit at the University of Sydney. So he was appointed Professor of Medicine and set up a clinical research unit which would really have a focus on using radioisotopes in clinical investigations. He employed a senior lecturer, Jim McRae, in the late 1950s after he returned from completing a PhD in medical physics at Lawrence's Donner Lab in Berkeley. So McRae was a physician, but went on to do a PhD in medical physics with Ernest Lawrence of cyclotron fame. So he was clearly exposed to the cyclotron at that stage and realized the potential that it had. In preparing this talk, I was surprised to learn that in 1961, the Department of Medicine at the University of Sydney purchased a positron scanner for brain tumor imaging for one of their neurosurgeons, Rex Money. And this is what the device looked like on the top photo and the sort of scan that came off it in the bottom photo. And this was used for a number of years with arsenic-74 as the tracer that would be used in the positron scanner. So this is possibly, I think, the first use of positron imaging in Australia. And it's also, I think, worth noting that this whole unit at the CRU in the Faculty of Medicine, which became, when it moved across the Missenden Road into the site to develop a nuclear medicine department, really grew out of a desire to use radio tracers to study function and medicine, whereas most of the other initial nuclear medicine investigations around Australia really grew out of endocrinology with a desire to study thyroid function and to treat thyroid disease. So this was quite different, as it was not interested so much in thyroid work but in general medical work. There are papers on the study of ascites and other chromium labeled ion ferrokinetics and so on from this early phase of this unit. And McRae was very important in establishing this, and he learnt a lot of this when he worked at the Donner Lab in Berkeley with Lawrence, to which he eventually returned in the 1970s. In 1963, he went on to publish a paper entitled Medical Use of Radioisotopes in Australia. And at that stage, he identified the need for a local cyclotron. So this is, of course, a decade or more before PET is even developed, but there was an obvious need that he recognized for positron imaging, as well as for the number of single photon emitters that would be useful to have that were produced on the cyclotron. And in 1968, Henry Wagner, who went on to become well known as almost the godfather of nuclear medicine, and David Kuhl, who was the first to attempt to investigate tomographic imaging in nuclear medicine, visited Australia. Wagner had been sent from Johns Hopkins University, where he had studied medicine, over to the Hammersmith in the late 1950s, and he saw the cyclotron in use there, and he was inspired to think about how this could be more used in medicine. Wagner returned to Baltimore, to Johns Hopkins, and set up a nuclear medicine unit there, and was among the first to perform a lung scan using radio-labeled macro aggregates. So a lot of this does go back to the Hammersmith and the early work with cyclotrons being the inspiration for using the cyclotron products in medicine and developing nuclear medicine as a specialty. So Wagner and Kuhl came to Australia in 1968 and talked about the use of short-lived gamma emitters, as you can see there. And in his memoirs, Wagner noted that on the way to an IAEA meeting in Vienna, Dave Kuhl and I spent 16 days in Australia. I'm not quite sure how visiting Australia is on the way from Baltimore to Vienna, but nevertheless they did. And this was a trip sponsored by the US Atomic Energy Commission and the AAEC. The purpose of our trip was to promote nuclear medicine in Australia. The Australian government operated a nuclear reactor and radiopharmaceutical manufacturing program that was supplying the country. Between the two of us, Dave and I delivered 48 lectures in 5 cities, together in Sydney, Melbourne and Canberra. I went to Brisbane and Tasmania alone, while Dave went to Perth and Adelaide, so they really did cover the whole country. One of the principal topics of our lectures was camera versus scanners. The Anchor camera had recently been introduced by Nuclear Chicago and would eventually replace the rectilinear scanner. But at this stage, these two gentlemen were identifying to the Australian government that there was a need for a cyclotron in Australia in 1968. So in the 1970s, the AAEC was in a wonderful position in developing new radiopharmaceuticals and distributing them on a daily basis from Lucas Heights to all Australian capital cities. This was done for free and on a daily basis. As I said, this was known as the Milk Run. It was internationally recognised at the time as an outstanding model of service and certainly helped to give a boost to the practice of nuclear medicine and its development in Australia. This is, of course, about the same time that the Society came into being in 1969. In 1970, the AAEC approved $850,000 for the in-principle acquisition of a cyclotron. Possible sites proposed included Lucas Heights and St George Hospital. The NHMRC supported the decision. So this is again still before tomographic imaging, before CT imaging, where nuclear medicine is seen as incredibly important in studying organs and tissues and systems that could not be visualized with planar radiography or with focal plane tomography. Soon after, however, Godfrey Hounsfield reported the first CT scans on the EMI scanner at the RSNA meeting in 1973, and things started to change. In 1974, the AAC suggested providing hospital facilities and building a mini hospital at Lucas Heights to complement the installation of a cyclotron. This was controversial, and I think many in the nuclear medicine community did not see this as being the best way to develop a clinical facility. The idea was really debated at this stage, wouldn't it be better to put the cyclotron into a hospital rather than the other way around? In 1975, Mike Phelps reported the first tomographic positron imaging device, brain scanning with FDG, again, this now introduces a new reason for needing and wanting a cyclotron to start to look at these sorts of scans. In 1979, again, very early on, the Austin Hospital requests a small cyclotron. As it's a small cyclotron, we assume that it's for PET studies, as PET was now being made commercially available with the ECAT3 system from EG&C Ortec. So we come to the 1980s, and in 1981, the State Ministers for Health in Australia support the in-principle acquisition of a medical cyclotron at their Darwin meeting. This was obviously a project that had been discussed for 10 years or so and had stalled. The big change came in 1983 when the Hawke Labor government was elected, displacing the Fraser Liberal National government. The reason it's important is the fellow on the right, Peter Morris, became the Federal Minister for Transport and Aviation. Peter was the brother of the head of nuclear medicine at RPA, John Morris. And soon after this, John was appointed to be a board director of the AAEC. And John was very, very vocal about the need for a cyclotron in Australia, having been around at the time and really being one of the leaders of nuclear medicine back when Wagner and Kuhl had visited in 1968. So 15 years later, still pushing for a cyclotron. The importance of this is that John now had fairly direct access to Cabinet in Canberra, and he could lobby for a cyclotron for Australia. So eventually the Commonwealth Government Departments of Health and the Resources and Energy established the Medical Cyclotron Committee to look at proposals from the Austin and a joint AAEC-RPAH submission. The deliberations were published in a paper in 1985 in the Medical Journal of Australia called The Medical Case for an Australian National Cyclotron Facility. And this set out the needs for both single photon emitters and PET. However, single photon radionuclide production was still the main argument for a need for a cyclotron in Australia. And so therefore this meant that it had to be a mid-sized cyclotron capable of producing charged particles, sufficient energy to produce iodine-123, thallium-201, gallium-67, indium-111, and so on. As a byproduct, it would have the ability to produce the PET radionuclides, which are generally made at much lower energies. And so the proposal was for a national medical cyclotron to be sited at a hospital and with a PET scanning facility on site. And eventually RPAH was selected as that site. What was PET doing at this stage? I mentioned that it had just become commercially available, but there were quite a number of PET scanners developed in research institutions that were not commercial. The French had a system. There was a system, time-of-flight system based out of St. Louis. There was a Scandotronic system from Sweden, which was commercially available, and there was the US-based system that Phelps had worked on. However, it was only used as a research tool. It had no clinical role at this stage. It was very expensive. It had very limited axial coverage. First systems only had 5 centimeter axial field of view. And it was predominantly used for neuroscience, looking at regional cerebral blood flow, neurotransmitters and receptor studies, and cardiology. And you can see the image on the right was from the front cover of Nature in 1983, showing the first time fluoridopa concentration in the basal ganglia of the human brain in a living individual. There were very few oncological applications, and certainly not many were envisaged at this stage. FDG was being used predominantly to image glucose metabolism in the brain and the heart. By 1988 in Australia, the plans for the National Medical Cyclotron were finalised. It had a budget of just over $20 million, not including the PET. A further $4 million for PET was to be funded by a $2 million grant from the New South Wales government, and then they needed to find $2 million in fundraising donations. So that was a large fundraising program at the time. Morris developed a very large overseas training program in PET, as no one in the country had any experience in the use of PET at this stage. This included physicians in nuclear medicine, psychiatry, neurology, cardiology, and so on. It included physicists such as myself, radiopharmaceutical scientists, and nuclear medicine technologists. And we were all dispatched to the Four Corners to learn at places such as the Karolinska, UCLA in Los Angeles, Hammersmith where I went, Jülich in Germany, Akita in Japan, the Institute of Neurology, University of Michigan, Ann Arbor, the Triumph facility in British Columbia, Vancouver, and the National Institutes of Health, and you can see a few of those there. Eventually, the National Medical Cyclotron was built and was opened by the then Governor-General Bill Hayden on the 13th of March 1992. In a few photos there, you can spot some characters that you probably recognise. Look at the underlined section in the text in the middle there about the ambition for this, because again, the PET was still to be used as a research device predominantly. And RPA's ambition was to begin with heart and brain studies of 4 to 6 patients only per week. They were going to use deoxyglucose and nitrogen-13 ammonia. And this would be transported from the nearby National Medical Cyclotron about 300 metres away from the PET scanner and sent across in a pneumatic tube. You can see the mission statement for the National Medical Cyclotron in the bottom right corner of the slide was to produce radioisotopes for the manufacture of radiopharmaceuticals, and that's predominantly referring again to the single photon emitters for the country rather than being predominantly about PET. The cyclotron that was purchased, as you can see on the right, was an IBA Cyclone 30, a 30 MeV machine. So 30 MeV protons could be produced in this negative ion system, and it promised a lot. It was able to produce 2 simultaneous beams which were supposedly able to be run at different energies, so that you could be manufacturing long-lived traces at high energy, such as the 30 MeV protons required for thallium, while at the same time producing the short-lived positron emitters. Whether it ever really achieved this is questionable, and it laboured under this problem for many years. At its peak, however, it was producing 70,000 doses a year of gallium and thallium, of course, which we now have to import because this machine was decommissioned in the mid-2000s. As I mentioned, the PET radiopharmaceuticals were transferred to the hospital on level 7 of the Albert Pavilion of RPA via a 360-metre underground pneumatic tube. At the same time as the Sydney Centre was being developed, the Austin PET Centre was also becoming a reality. PET had been championed from the early 1980s by their Professor of Medicine, Austin Doyle, and eventually John Mackay, Head of Nuclear Medicine, was called upon to lead the project. Their centre was established in 1990 with funding from Victorian Commonwealth governments and the Austin Hospital. It was different to the RPA model because it only sought to make positron-emitting radionuclides for PET. It wasn't going to produce any short-lived gamma emitters for distribution around the country. The funding came, as I mentioned, from Commonwealth Government, Austin, and the Austin Hospital's Foundation and the fundraising arm. You can see the camera on the right there. You might recognise it's the same as the one I showed you in the pictures at RPA. And at the time, the RPA and Austin Hospitals combined their heads to purchase the best machine that was available, and that at the time was the ECAT 951, and we both sites bought the same machine. The first PET scans were performed in Australia at the Austin on the 8th of July 1992, and here you can see the initial team, physicians and technologists, professors of medicine, as well as the patient herself sitting there, and the first scan you can see of really quite acceptable quality. RPA's first scan was performed less than a month later, a PET myocardial viability scan, and soon after that, the first brain scan was performed, as you can see on the right, in September 1992. So at this stage, PET, as I mentioned, is mostly a research tool with a couple of clinical applications in epilepsy and myocardial viability, but not much else. But it started to change around 1991 when the UCLA group came up with the concept of doing whole body scanning by crab walking the scanning bed in the patient through the limited axial field of view of the PET cameras, which at the time were 10.8 centimeters on the first machines that we bought. And Henry Wagner again comes back into play and writes this very important article about clinical PET, realizing that PET was not going to have any future unless it had a clinical application. And the final sentence in his article that you can see here from the Journal of Nuclear Medicine says that histopathology remains the cornerstone of cancer diagnosis and treatment, but in vivo chemistry is an idea whose time has come. And this is when we start to see the introduction of the oncological applications of positron emission tomography. So where are we at today? Well, there are a large number of medical cyclotrons dedicated in Australia. This map, which I've recently updated, shows you where they're located and what they have. There's also a new proposed machine in Western Australia, the P in the Circle, as well as a new one proposed for Melbourne. And this is an important development because as of April this year, the federal government announced funding, part funding towards a mid-sized cyclotron in collaboration with Monash, GMS Australia and Telix that will be developed at the Monash Biomedical Imaging Centre. And importantly, this will start to make those single photon tracers again that we had to import for the past 15 years or so. And of course, we all have experienced the impact of logistics problems in that regard in recent years. So we look forward to this coming online in the next few years. So to conclude, while it took us a long time from first flagging the need for cyclotron to actually introducing one, some 30 years or so, and it seems to have been a stuttering and a stop-go process along the way. We have eventually achieved what we wanted, and now have, I believe, adequate cyclotrons and facilities around the country to support the more than 100 PET-CT scanners that there are today. Thank you.